morning. Hopefully the button's going to work. So yeah, just a brief intro because various people asked me about cars on the way in. So Rolls-Royce PLC, the only connection is we own the trademark for Rolls-Royce motor cars, but we've licensed that to BMW. So we have 5 businesses, dominated at the moment by civil aerospace, about 50% of our turnover. And that's the business that I'm going to probably talk most about. But also very strong businesses in defence aerospace, marine, power systems and nuclear. And if you want more details, please go and have a look at our website. So AI and robotics, well, I thought rather than going into lots of depth about specific technologies, I'd try and paint a picture about how I think they can affect engineering through the entire life cycle. So starting with design, manufacture, assembly and test, operate in service, and then maintenance. And there's a whole panoply of technologies that can really, I think, make a huge difference. And one of the important things with all of this is feedback to design. So how do we keep improving our designs and optimizing our designs? And I thought perhaps by way of context, I brought a bit of hardware with me just to give you a sense of some of the challenges that we face. So Rolls-Royce in the next few years will basically provide over 50% of the world's wide-body aircraft with engines. This is our latest engine, the UltraFan, that we're developing. And to give you a feel, we spend over £1 billion a year in research and development. And a huge emphasis of that is about improving the environmental performance of those engines. So fuel consumption, emissions, NOx, etc., and noise, absolutely critical. And we really push the bounds of technology. So right in the heart of that engine, this component here is a turbine blade. This component, to give you a feel, will generate the same power as a Formula One racing car. There's between 70 and 90 of them in an engine. It has to operate for at least 5 years between overhaul, flying 10, 12 hours a day. When it's running at several hundred degrees above its melting temperature. And the centrifugal loads on that is the equivalent of hanging a London bus off every single one of those. So you can start to appreciate some of the engineering challenges, and that's one of just 18,000 components in the engine. And of course the engine has to start, we all expect it to start, and critically it has to be safe. So where can AI help? Well, these use really sophisticated materials that historically have taken perhaps a decade to develop. We're now looking at things like use of AI to speed up research. Material science, I think, is a particularly interesting area. So how do we use AI to pull together that huge range of knowledge and come up with different hypotheses? Doesn't remove the need for the researcher, but makes their job faster. We're using it in all sorts of simulations. So yes, we can run computer codes on some of the top high-performance computers. We use Archer, we use Hartree, but we still have some limits as to what we can model in the physics. So how do we marry that with the huge array of test data? So these engines, we run all sorts of development tests before they go anywhere near the public, acquire enormous amounts of data. Well, we're now starting to use AI systems to bridge some of the gaps between the physics-based modeling and what we see in the experimental world. And we're even using them to come up with new designs. So historically, we've used experts with decades of experience, PhDs, long expertise. We can now use computer simulations to simulate all sorts of different designs, get AI systems to learn about the behavior and find new optimum solutions. And then, of course, things like VR and AR are important in terms of visualizing those designs. And critically, I suppose, as well as improving the performance, is speeding up that time to market. So for us, it takes longer to certify and develop an engine than the airframe. So anything we can do to shorten that time frame gives us more market access and opportunity. When we go over to the world of manufacturing, perhaps more focused here on robotics, obviously 3D printing gets a lot of press. We're doing work in 3D printing, still some challenges for aerospace, particularly around some of the materials properties and development, but that's an exciting technology. One of the challenges I think we have is, in our world, the engines we produce maybe a few hundred a year. So we're not in the sort of mass automotive manufacture. So some of our factories, you will still see very manual processes because the robots of today are not sophisticated enough, flexible enough, or at a price point that makes sense. But at the other end, these components we produce more than 100,000 a year. So some of our factories now are fully robotic, fully lights out. But I think the potential for robots to start taking over some of the more manual tasks that we have today, particularly in the more low volume specialized areas, is going to come. And then we're using systems obviously to help with the quality control and the conformance. So we do a lot of work around image processing, sort of AI systems to understand, so we can build engines and then monitor them, check that all the parts are in the correct place. And that's, I think, a useful addition to the standard aerospace quality control systems. Assembly and test. So I spoke about the fact that we'll build a number of engines, and in fact we'll even destroy some of those to prove the capabilities before they go anywhere near the public. A range of different AI systems that we're using actually already in the assembly and test. So on the top left, so in the middle of the engine, this component turns a shaft that rotates at over 10,000 RPM, and that shaft connects to discs. And so it's really important for the engine that we really optimize the balance of that disc to minimize any vibration. And we now use AI systems to take all of a series of components that you might have in your factory and work out which are the optimum set of components and the optimum orientation of those components to minimize the vibration using a machine learning algorithm. We're using them on lots of different ranges of image systems. So the picture in the middle here is a picture of a gearbox during one of the destructive tests that we perform on the engine. So the big fans that you see at the front, a certification requirement is essentially we run the engine to full power and literally blow up a sort of explosive bolt at the bottom of the blade. And that blade, when it's running, has about 70 tons of CF load, and we have to prove that the engine can safely contain that and run down. So it's equivalent to stopping a family car on the motorway in about half a foot. So that causes, as you would imagine, quite a bit of vibration to the rest of the engine. And the gearbox, we have to prove, stays safe, all the connections, all the hydraulic fuel systems, etc., all intact, all the harnesses are safe. And so one of the tests we did recently, we had a number of high-speed video cameras pointed at this gearbox from different angles. And we were able to use some image systems to reconstruct the 3D behavior of the gearbox during that quite rapid and violent event, feed it back into the original stress modeling, and actually use that not only to certify that engine, but also to prove that we could then extend the envelope. So when we wanted to come up with a higher thrust variant, we didn't need to redo the test. The test, by the way, writes off an engine, so it's more than £10 million, so you don't really want to do that very often. And then the system on the right, so actually that's an X-ray looking inside an engine when it's running at full power. So we have a portable X-ray. It's the most powerful portable X-ray in Europe. It's capable of a medical X-ray at about 3 miles away. So part of the test, we have to put lots of lining in the test bed, and we point it away from our employees and make sure that we can do the test safely. But even with that power of X-ray, you can imagine looking through an engine, the quality of image is quite difficult for a human to understand. So we can now use some of the imaging systems with neural network sort of learning to understand the behaviors of specific features and relay that back to the models. So engines, of course, they get hot, they get cold through the flight cycle. There's different loads on them, so although the movements are relatively small, components do move within the engine. And understanding that movements really helps us optimize the performance of the engines. In terms of in-service, well, I guess Rolls-Royce has got 20 years experience of data analytics. So a fundamental part of our business proposition is we sell engines to the customer, but then we effectively charge them $1 per flying hour rate, and we look after the maintenance. And an engine through its lifetime will generate 3 to 4 times the original equipment revenue in aftermarket sales, and actually that's where we make the money. So it's a really important part of our business. Our very early engines basically took a very small amount of data per flight, so perhaps 20, 50 kilobytes of data, just taking snapshot points at key flight conditions like takeoff, climb, cruise, descent, landing, engine start, engine stop. But the latest engines with much more sophisticated systems, of course, can acquire huge amounts of data. So this is vibration data, pressure, temperature, speeds, oil system conditions, and so on. Historically, we used to basically, whenever we brought an engine into the shop, if we had any kind of findings on that engine, we would go back and reanalyze all the on-wing data and try and look for trends. And we built up a library of trends based on our knowledge of the engine. That means that we can predict in advance potential problems with the engine and take action, which is great if that problem's already happened before, but it's not much use on a new engine that may have a new problem that we may not have seen. So now we actually use neural network systems that self-train for every single engine, and over the initial phase of running in, they learn how the engine behaves and continue to learn, and then they can flag up any deviations from that learned behavior. So as well as having all the sort of systems based on known events, we can now use this as a means of catching events that we haven't even seen before. And the statistics sort of speak for themselves. When I joined the company, I think we had about 12% market share. We're growing to 50%. The actual number of events that we have over that time has basically stayed flat. So we've had huge improvements in reliability, and some of these technologies have helped with that. And then in terms of maintenance, so as I said, we basically make our money by keeping engines on wing and flying. So the objective is spend as long on wing as possible, and then when you come into the shop to do the work spoke, do the amount you need to, but no more. So really important that we try and keep engines flying. We're doing some interesting work using borescope images. So within an engine, it's a bit like keyhole surgery. We have some holes, literally 4 mil in diameter, where you can stick a mini camera in and take quite a difficult, grainy, grey and white picture. So image processing with those kind of pictures is actually really challenging because there's no distinct features, it's not in colour, and the image quality is limited by the fact you've got to fit this camera through this 4mm hole. We're now using systems where we can measure clearances, even using the shadows from the light cast by the camera system. And then looking forwards, we're going to be able to measure things like any damage. So if we have foreign objects that get picked up off the runway and go through the engine, we can now start to understand that and relate that back to the models and hopefully clear the engine to continue service. If we do need to do further work, things like snake robots, and we do borrow blending. So through that 4 mil hole, we can actually put little robots in and start to take action and in fact blend out some of the cracks. And then interesting area going forward, things like origami robots. So I think in future the potential for really, really tiny robots to actually go in and potentially be remotely or self-controlled. When we come into the shop, so the off-wing, massively changing technology for me is around 3D scanners. So we've used 3D scanners for a while, but the scanners typically were sort of this kind of size. You needed a robot to lift them. Very, very precise, but obviously quite limiting in their use. In the last 2 years, we've seen 3D scanners like this one start to become available, using some of the technologies you find in your mobile phone, multiple cameras, gyro systems, and we can scan components literally to an accuracy of 0.05 millimeters and in full color. And that gives us ability back to feeding all this information back to design. If we can relate the information we get from these components when we bring them into shop to how the engine's actually been operated in service from all that on-wing data, I think it's got huge potential to enhance our ability to design for different types of missions, optimize how the engine behaves in service, and optimize exactly what we do when we bring the engine into the shop. So hopefully that gives you, in just under 15 minutes, a little view as to how we're using AI and robotics right the way through the design life cycle.
And the bold prediction?
The bold prediction, I think it's going to be a rapid change in the use of particularly imaging systems going forward. So today we have lots of manual inspectors looking at components. In the future, I think that will be highly automated with automatic feedback to the design and self-checking to say, yes, this component can be fitted, refitted, repaired, replaced, and all of that done seamlessly. Thank you very much.